Welcome! My name is Loido, and I am presenting you the onboard model-based prediction of tram braking distance. In this paper, we present a method for the prediction of a braking distance. Our method can accurately predict the braking distance based on an onboard simulation of a mathematical model of braking dynamics and measurements from onboard sensors. In particular, as you can see in the diagram, we focus on the prediction of braking distance for trams, which are light rail vehicles designed mostly for passenger transportation in urban areas. The motivation for the work presented in our paper is the development of a collision warning system for trams. Collisions of trams is not a marginal problem as you might think. Just Prague Public Transit Company has been registering well above 1,000 collisions every year. As you can see in the photos, these tram collisions are with other road vehicles, trams, or even pedestrians. In some situations, mainly in the case of tram-to-tram collisions, the tram driver's inattention is the main reason for the collision. Such collisions could be avoided by warning the driver sufficiently in advance of an imminent collision, possibly even automatically applying the brake. In a simple case, it is intuitive that to avoid a potential collision, we need to warn the driver when the braking distance, plus some safety margin, is higher than the distance gap. We therefore need to estimate the distance gap and predict the braking distance. At first, you might wonder, why is there a need for a more sophisticated method for prediction of braking distance than use of this basic formula? This formula is of course inaccurate, since the maximum braking acceleration, ABR, is not constant during the braking and can vary with changing adhesion conditions or weight of a tram. For collision warning, one can, however, always choose some conservative value of the braking acceleration or add a higher safety margin. Such an approach would work, for instance, in the case of heavy rail vehicles, but not for trams. Take, for instance, the Tatra T3 tram, which is by the way one of the most produced trams in the world and is still used nowadays. With approximate passenger capacity 100 people and curb weight 16 tons, the actual weight with passengers can be some 50% higher from an empty tram. This of course drastically changed the braking dynamics. Furthermore, in cities with dense tramway traffic, the distance gaps between trams could go down to less than 1 meter, as you can see in the picture, where 3 trams stop at the same moment at tram stop. If we would set the conservative value of braking acceleration or safety margin and use the basic formula, the collision warning system would in general give too many false alarms. It would definitely be better to avoid at least some big collisions with the collision warning system than overwhelm the driver with warnings. Therefore, it is necessary to predict the braking distance more accurately. In our research, we don't have ambitions to prevent all collisions. We focus only on the development of a tram-to-tram collision warning system. The advantage is that from the known absolute position of both trams measured by GPS, we could use direct communication between the trams, so-called V2V communication, to compute the distance gap. No sensor, such as a radar, is necessary, which makes our solution cost-effective. In the city of Ostrava in Czechia, such infrastructure for V2V communication is already available. That is, all trams are equipped with a V2V communication unit developed by Herman Electronics. You can find more details of the V2V communication unit on this link. We are now collaborating on the collision warning system with the City Public Transit Company in Ostrava. And we already have some preliminary results of such a collision warning system from experiments with a real tram. The task was to give a warning to the driver of an imminent collision, not too soon, but also not too late, so when the driver starts braking, the tram finally stops exactly at the desired position marked by the cones, like in the picture. The whole collision warning algorithm was implemented on V2V communication unit on board a tram with a connected loudspeaker to give the warning. If you are interested, you can find a more detailed description in the draft of our new paper available at this link. Let's now watch the video from the experiments.
Close.
We could see that only in the first experiment the tram stopped precisely at the desired position, but not in the second and the third experiment. There are two main reasons for this. The accuracy of the warning system still depends on sensor measurements, like GPS, which are sometimes inaccurate. Also, the total braking distance depends on the driver's reaction time, which was not consistent in all experiments. So surely, in a real deployment of a collision warning system, some safety margin should be set, but also, in some serious situations, the driver can use the emergency brakes, which can significantly reduce the braking distance. Regarding the prediction of braking distance, results from the experiments are promising. Here, on this graph, you can see that the prediction of braking distance was in general quite accurate. When the driver had started braking, the predicted braking distance, the blue line, was for specific speed almost the same as the final measured braking distance, the red crosses. Also, for comparison, the yellow dotted line on the graph is the braking distance computed by the simple equation. You can see that our method is significantly more accurate for higher speed. Now, let's go back to the prediction of the braking distance. Here is the diagram of the proposed method. There are several essential tasks. First, on board a tram, we obtain an absolute position and speed from the GPS module and acceleration from the inertial sensor. Using the Kalman filter, we can then estimate the position and the speed from the measurements and the data from the digital map of the track. Also, some physical parameters which can significantly change the braking dynamics, such as weight or adhesion parameters, need to be estimated. Lastly, we use the model of dynamics of the tram developed in this paper to simulate a tram's motion, from which we finally acquire the braking distance. Let me now describe in more detail the model of dynamics. Because we are interested only in the longitudinal motion of the tram along the track, it is sufficient to use a so-called quarter model of dynamics. The model can be illustrated by the diagram on the left with its bond graph on the right. The full set of equations and detailed explanation can be seen in the paper. First, the torque generated by the motors is proportional to set throttle notch. The power from the motors is then transferred into the wheel's motion, which, in turn, through the adhesion with the rails, cause the longitudinal motion of the tram. The tram is also affected by the resistive forces, the propulsion resistance, computed by the Davis formula, and force, Fs, given by the slope of the tram tracks, and the normal force. With all these components in the model, we can predict the braking distance for various cases. By selection of the throttle notch, we can choose the intensity of the braking. With different adhesion parameters, we can include changing track conditions that affects the amount of power transferred from the wheels to the longitudinal motion. We can also take into account variable weight due to the actual number of passengers in the tram with parameter m. Lastly, we can include a non-zero slope rail track by changing the parameter theta. On this graph, you can see how braking distance can significantly change with different parameters such as higher weight, non-zero slope track, or worse adhesion conditions. We fit the model for a particular tram type and then verified the identified model with real experiments. Here, on the figures, you can see the comparison of the simulated speed and acceleration with measurements from real experiments. We display two scenarios, figure on the left and figure on the right, in which we instruct the tram's driver to follow the predefined sequence of the input. The same sequence of the input was then set in the simulation. You can see that the model outputs, the blue lines, match the measurements, red dashed lines, for both speed and acceleration. If you are interested, you can download the model in Simulink at the MATLAB file exchange. To sum up, the algorithm to predict the braking distance proposed in this paper is the following. First, the measurements from onboard sensors are acquired. We use the position and the speed measurements from the GPS module and acceleration from inertial sensors. These measurements are then used in the state estimation, for which we use the Kalman filter. The state estimation's main output is the longitudinal speed of the tram, which is then set as initial condition in the simulation of the model of dynamics. With set braking intensity and some other parameters, we can obtain the braking distance as total traveled distance from the start of the simulation until the simulated speed is 0. In our research, we use the prediction of braking distance for the collision warning systems for trams, but of course, the presented method can be used in other applications, for instance, energy optimization of trams motion. We are still working on improving this method. In particular, state estimation heavily depends on GPS measurements, which can be inaccurate in some cases. Also, we haven't dealt with an estimation of the total weight and the adhesion conditions. We couldn't address these problems in the presented method since we were limited by available sensors in the tram. However, in recent months, we have upgraded the hardware and the software used in the trams, which now allows us to get additional measurements from the tram's internal sensors, namely the wheel speed, the electrical current in motors, and also in newer trams, even the data from cameras in the tram. The wheel speed and the current in motors could improve the state estimation and the estimation of adhesion parameters. Furthermore, we would like to test the estimation of the number of passengers in the tram using the cameras, which, in turn, gives an estimate of the total weight. Such experiments are now in preparation. Thank you for watching our presentation, and if you have any questions or comments, feel free to write me an email.